Alright, so in this tutorial we're going to introduce the concept of torque, the first of our quantities that directly relate to rotation. Very quickly, torque is a turning force. It's very much related to linear force we've talked about, but there's an extra component to it, something called a lever arm. So let me give you a little background before we get into the definition of torque and equations and then some sample problems that we're going to use to solve. We'll try to get through as many as possible in the 15 minutes and we'll pick up from there in class. All right, so we talk about this in class. Up in this point in physics, where a force is acting on a body has not been given any consideration. What mattered to us was the magnitude and direction. Okay, we only cared about how much force was acting and what direction it was acting, and looked at other forces, and then we could find net force. We could apply the second law. But nature is a little bit more complicated than that. We care about, in certain circumstances, exactly where on the object it's acting, because it can give us more than linear, it can give us some rotational. Okay, so now that we have a more sophisticated understanding of a body's mass can be distributed, i.e. we understand the concept of center of mass, we can now look at the effects of the wear of forces. All right, so look at this diagram right here. I have some body, here's the center of mass right here, and there's some generic force acting on it to the right. And not only is it acting to the right, it's acting towards the top of the object. Okay, so what we want to look at is not just the force, but something called a line of action. So what do I mean by that? If we take this force, this arrow is just an arbitrary value of direction and kind of an indication of magnitude. We can say it's acting somewhere along this line. The line extends back as far as we want it to go and forward as far as we want it to go. And this is an important consequence. If it does not pass through the center of mass of the body, then the body will feel a rotating force. Okay, otherwise known as a torque. So let me try to explain that a little bit more. And the symbol for torque is the Greek letter tau. Kind of looks like a T with some squiggles in it. All right, lowercase. So in other words, here's the center of mass of the body. If we extend our line of action here, it does not pass through the center of mass. So it's going to want to turn in a clockwise manner. Another example we could do is something like this. Let's say we had a force acting like this on the body. If we extend the line of action back, it does pass through the center of mass. So it's as if the force is acting directly on all the mass, so it's just going to change linearly. If I do a third example where I have a force that is, let's say, acting like this, then if I draw a line of action, it does not pass through the center of mass. So the consequence of that force will be to turn it, as well as perhaps move it forward linearly. Depends on what other forces are present, whether move linearly or not, or turn. All right, so we're going to see that's very important to locate where the force is acting relative to a pivot point. Sometimes a pivot point is the center of mass, other times it isn't. Okay, so the consequence of a torque, what do we care about, is to rotate a body about a pivot point. All right, so now we want to talk about this pivot point a little bit more. And then in the process, you're going to cause angular motion, of which more we're going to talk about later. For today, we're going to focus on static situations where there is no change in motion, but there are definitely torques acting on something. So the pivot point can take on two general forms, okay? As a hinge, or sometimes called a fulcrum, depending on the situation. If the body is attached to something else, i.e. hinged, where it's free to rotate about that point. Okay? If there is no hinge or fulcrum, then the pivot point is almost always the center of mass. So in many problems, it'll be pretty clear what your pivot point is. But sometimes you got to think about the situation you do. Is it the center of mass that we're going to rotate about, or is it going to be a hinge? So if we go back to our original example, if this block were sitting in free space, not attached to anything, then the pivot point would be the center of mass. If on the other hand, let me draw it again right here. Let's say we had the hinge right there that was pivot, then when I had my force here, okay, the line of action does not pass through the hinge, the pivot point, so there's going to be a torque. As such, if an object is balanced, in other words, it's not rotating, Or if it's moving at a constant speed rotationally, all right, then we know that the net torque must be 0. So it's a similar law as the second law of motion, or the first law of motion. If there's no net force, an object continues to do what it's already doing. So if there's no net torque, an object will continue to do what it's already doing. All right, so directions of torque. Generally, when you're talking about rotation, it doesn't make sense to talk about up, down, left, right, but rather we talk about clockwise or counterclockwise. I'm going to write counter CW for counterclockwise. And the general sign convention is if something is rotating clockwise, you guys know what that means, I hope, right? The old clocks would be going around like that. That's a negative value for torque. And if it's counterclockwise, we give it a positive. All right, so let's look at an example, conceptual example right now. So suppose I have some beam right here, and my pivot point is on this fulcrum. Okay, so it's not quite a hinge, but it can rotate about that due to various forces. So I have 6 arrows indicating forces, and we want to label them as a positive torque, a negative torque, or 0 torque acting on it. Some situations are pretty clear. Others, it's not so obvious. So we want to go back to the idea of the line of action and ask if it passes through our pivot point. I know initially I said the center of mass, but what we really mean is the point about which you can pivot. So in that case, this is the point we're interested in, not the center of mass. Right here, I'll put an X, would be roughly the center of mass of that beam. All right, so if I look at this leftmost arrow, if I extend the line, it passes through the pivot point, so there's 0 torque due to that. That's simply a linear force. If I'll go clockwise, so if I look at this force, it also passes through my pivot point, so there's 0 torque due to that. It's not going to try to turn it because it's passing right through the fulcrum. If I go to this force right here at an angle, I see that if I extend my line of force, that it is definitely not passing through the pivot point. So there is a torque. Now the question is it going to be clockwise or counterclockwise? We'll talk about this a little bit more later. But there's 2 components to this force. There is a rightward component and there's a downward component. The rightward component passes through it, so that does not contribute to torque, but the downward component does contribute to a clockwise torque, so that's a negative torque. All right, if I go to this arrow, it's clearly pushing up, not going through that, and that's going to give us a counterclockwise, so it's positive. The center of mass, all right, in other words, the weight of the whole beam here is concentrated at this X, so it's trying to pivot it about the fulcrum in a clockwise manner. And this one is also clockwise, okay, because this is trying to rotate it that way. The hardest part, I believe, in trying to do torque problems is just identifying what the where the force is acting relative to the pivot point, because that where we have to quantify to actually calculate it. So let's now turn our attention to calculating torque and then spend more time doing problems. So when calculating torque, you got to do a few things before you just plug things into an equation. You got to know the magnitude of the force. All right, that's generally pretty straightforward. The second part is the hard part. How far from the pivot point is the force acting? Okay, so we have to talk about that, and that's called the lever arm. And we're going to give this symbol R perpendicular. Okay, so the lever arm is a length. It's a distance. We give the symbol R, and that very important thing here is a perpendicular. So the direction of the force relative to the lever arm is 90 degrees, and that's where the perpendicular comes from. So this is a cross product. We want a combination of force and distance, but where the forces and distances are perpendicular. So our equation for torque in general, tau, is equal to F cross R. That X is multiplying. That's a cross product. Okay? What that translates to in the most general sense is simply the F value times the R perpendicular value, which is FR sine of the angle. Okay, sorry that got outside the box there. So you will see in your reference tables the equation for torque is this. They're just trying to tell you we want the component of R perpendicular to F, or the component of F perpendicular to R. It doesn't matter which one you do. The units. Well, if we're doing a force times a distance, you might think it's a Newton meter, but Newton meter is already taken up by work or energy. So since this is a very different concept, the way of expressing it, not to confuse with work, is a meter times a Newton. And when we're dealing with masses informally, and sometimes we can get away with what's called a centimeter times a gram, because a mass can be a substitute for the force of gravity. We don't have to have it in newtons to get an idea. And again, important, torque is a cross product. So we must use perpendicular components. So in the 5 minutes we have remaining, let's try to do some problems. Okay, so I've got a diagram of a door looking from above, and we have a hinge point right here. And there are 1, 2, 3 forces acting on in various directions, and we want to calculate the torques due to all from each of them, and then calculate the net torque. All right, so let's do, and each force is given as 10 newtons. Okay. So the trick is, what's the lever arm, so that we can calculate the torque. So if I take F1, I draw, in other words, I want to know how far away is that force from the pivot point in a perpendicular direction. Well, this one's pretty straightforward. If I do my line of action, it passes through the pivot point, so the lever arm is 0. Therefore, there's no torque about the hinge due to F1. It will try to push the hinge. It'll put some force on it in a linear fashion, but there's going to be no turning force. If I look at F2, all right, I can see that the force, if the force is definitely not passing through the lever arm. So what I do is, to get the lever arm distance, is from the line of force, I draw a line perpendicular to the line of force, whatever it takes me. So that's pretty clear that that distance, R2, is going to be the 0.8 meters. Okay, so 10 times 0.8 tells us we have 8 newtons of torque due to F2. And that's the easiest thing to visualize. That's nice and perpendicular. And in case 3, or force 3, we've already seen this before. Since this is acting, if we pass the line of action through there, the lever arm is also 0. Even though this force is the full length of the door away from it, it's not acting perpendicular to the pivot point, so there is no torque there. Okay, so our net torque, very simple, 8 newtons. And if we want to get technical, this is a counterclockwise, so I call it counterclockwise CC. So this is a positive 8 newtons. All right, let's look at a little bit more complicated problem. Let's realign that. All right, so we have the same situation, the door. We have 2 forces now, but they're acting at angles. Okay, so the forces are given, so we want to find the perpendicular component of the force for the lever arm so we can calculate the torque about the hinge. All right, so let's take F1. So F1 is acting up and to the right, but we want to find the lever arm. So what we want to do is, we could do a line of action. Don't write this on. Don't, just let me follow my reasoning here. I could do a line of action, and I could draw a R perpendicular to that line of action and try to calculate that. That's going to be kind of a pain to do here because I don't have easy angles. What I can do instead is take F and break it up into components. There's a component here and there's a component here. And I'm going to call this F perpendicular rather than call it Fy. Okay, so it is this component that is perpendicular to this lever arm, which I'll call R1, and that's going to be 0.5. So we know that's going to be 0.50 meters. So now we want to find the perpendicular component. Well, if I do a simple little trigonometry, I will find that the F perpendicular is nothing more than F of the sine of 60. You could do F cosine of 30, but that would give the same answer. Okay, so I'll let you work that out, why that turns out to be F sine 60, because, well, so this, when we do the calculations, is 34.6 newtons. So we multiply it by a lever arm of 0.5 because it's acting 0.5 meters from the hinge, and we get a 17.3 newton torque. And we can ask ourselves, is it clockwise or counterclockwise? That looks like it's counterclockwise, so that's positive. All right, same idea in our 30 newton. So here is the point where it's acting, so I'm going to break it up into a perpendicular component and, if you will, a parallel component, but I'm not really interested in that. So our lever arm, since it's acting way out here, is going to be 1.2 meters away. And again, the perpendicular component is going to be F sine of 30, and that will give us 15 newtons. So if we take 15 times 1.2, I get 18 newtons of torque. Since it's also counterclockwise, all right, then we simply add these two up and we get a net of 35.3 newtons of torque. Okay, so I'm going to stop right there. The next problem is basically the problem we did with center of mass. Remember, we had the ruler with the masses hanging on it, and we found out that the center of mass was 31. So if we put a pivot point right there, a fulcrum, what we want to prove is that the torques due to the center of mass and this guy are balanced by the torque from that one. So when we come into